Great, so I think it's about time to start. Welcome everybody, thanks for having me. My name is Ralf Böhme. I work for SerNet, I'm a member of the Samba team. And it's great to not only be attending the conference, but also be able to give my presentation. And as some of you may know, last year I've been at the conference, but I was sick the whole conference from Sunday till Wednesday the week thereafter for 10 days. So hopefully this year, fingers crossed, standing here and giving my presentation. And I want to give an outlook into some research and development that I've been doing over the previous months. And this is going to be like a looking up into the sky, Samba in the cloud, contrast to what Metz's presentation, previous presentation has been, like a deep dive into all this nitty little crazy stuff in the Linux kernel that we can use for performance optimizations. So a quick outlook. So this is basically about how can we bring Samba in the cloud? What are the challenges that we are facing with current Samba? Is there anything we might have to adapt or change with regards to elasticity, scalability, and things like that? We will sooner or later then discover that this has to do with the database that Samba is using for storing the session and file handle state. So we will be looking into distributed databases. I will present some benchmarks, results and conclusions in the end, and then a Q&A session at the end. If you have any questions, just feel free to speak up anytime and ask questions. So, scaling Samba in the cloud. So, the dream is like having a really scalable Samba server running in the cloud with hundreds of nodes supporting hundreds and thousands of clients, highly scalable, having that run in the cloud. I don't know how many of you are familiar with Azure SMB, so the file server from Microsoft that is running in Azure, in the cloud, an implementation using Azure Cosmos DB, a database for all the file handle and session state, and then in the back end using blobs and stuff like that for storing files and so on. And this is a really scalable solution, and Microsoft is really successful with this. So the question is this something that we can achieve with Samba, with current Samba, or maybe what do we have to tweak and change? And so in this presentation, I will try to look into what are the specific bits in Samba currently that are maybe not really suitable for this kind of elasticity and availability requirements that you have in cloud. So, coming to the problem that we might be facing with current Samba, if we put it just as is in the cloud. So Samba uses a database for file, handle, and session state. So on a standalone file server, this is called our TDB database, and on a Samba cluster, which this presentation is going to be about, clustering Samba, we use our CDDB clustered database. And CDDB, as I see, has just certain consistency and elasticity limitations. So basically, CDDB, while being very fast, it is so fast because it doesn't replicate data, at least not for the performance-sensitive databases that we care about. So it just stores a copy of file handle state data that we have to maintain in Samba on a single node, and that's basically it. And that way it can be very fast. And this has worked extremely well. I will share some numbers on a later slide. So the use case for this is basically like a high-performance NAS in a single data center. But this is not really suitable for cloud SMB at scale. So from what I remember, the real-world scalability limitations that vendors have spec'd out for products using Samba clusters is like up to a cluster up to 60 nodes supporting up to 50,000 clients, which is a lot. But if you want to go beyond that, like say you want 1 million clients, you want more nodes to support that number of clients. How can we go there? How can we get there? And also elasticity, which means as loads on the cluster is higher or lower, can you scale with the demand, right? Can you easily add more nodes to the cluster or remove nodes if the load on the server is going down? And the problem here with CDDB is that changing nodes, or adding or removing in CDDB causes a full, expansive database redistribution. So you basically have a complete stop of the database. It's doing its magic to redistribute all data. And that can take, depending on the size of the database, on the load of the server, can take quite some time, right? So this is really not that optimal. So what are the very high-level building blocks generally for a clustered file server? So basically, of course, we are sharing a file system, right? These days, we are just on a cluster still sharing a clustered file system like Ceph, commercial GPFS or Gluster or Luster or whatever. Maybe in the future, S3 object storage, but that's a completely different topic. How would we be able to integrate with something like that and build a file system on top of that? That's really not what I'm going to look into this presentation. This is basically more about the database part. Right, so I'm not going to look into file systems. Hopefully the file system community will solve that problem for us, right? So Ceph community, go, make it scalable, elastic, and so on. And we will just consume that. And then we are back to our problem of what database do we use in a scalable Samba file server in the cloud, right? So we need a distributed database. Can we use just CDDB or what else? So as mentioned before, so CDDB, as I see it, the main core feature is it's just fucking fast, right? Do we have the numbers here? Yeah, I put them there. So what I've seen in benchmarks that I've been doing all time over the last weeks and months is you can drive up to 60,000 open and close operations per second with a few thousand clients, a small CDDB, Samba cluster, just 3 nodes. And this is very, very heavy on very heavy workloads on the database, right? Because for every, so open and close means SMB open and close request to open a file and close. For every of those operations, we hit the database. We have to check for a record, we have to do some locking, we have to update the record, we have to put it back, and all that stuff. So this really tortures the database. And CDDB is really able to do this very fast. But as mentioned before, it just can't do this because it just doesn't replicate the database records in the cluster. It just stores a single copy. Which is, by the way, a problem also for implementing SMB3 persistent handles in Samba, right? But of course, for persistent handles, you typically would like to have a client connected to a node. So there is a file handle. There is file handle state stored in a database only on that node for CDDB. So if that node crashes and goes away, the client will connect to another node, and then for a persistent handle, for really transparent failover, it would go to that server and say, okay, I want my handle back. And then the server would have to go to his database and fetch his record. But unfortunately, it's gone, right? Because there was only a single copy. Right, so that's the kind of two-sided sword. It's fast, but it doesn't replicate, so there are some limitations. Like mentioned before, real-world scalability, I mean, this is what it's spec'd out. It might be able to support more demanding workloads, but the elasticity, as far as you can see, is probably the larger problem. And also CDDB has no support, I mean, because it doesn't replicate data anyway, for something like having multiple data centers or multiple availability zones, right? Where you want to make sure, okay, you have one data center in one region, but what about if that whole region dies, right? You want to fail over to another availability zone in a completely different region, like say on US West Coast and US East Coast. And all this is not possible with CDDB. So the idea was, okay, so what? Can we either fix or improve CDDB? Or maybe, I mean, it's year 2023. There is the cloud since 5 or 10 years. And like 15 years ago, started an industry effort where there's been put a lot of research and development into distributed databases to support cloud-native scalable workloads, right? So I did just sit down and do some research into what distributed open source databases are out there that we could use. And I think I have it on the next page. So this is just a few of them, right? So these are like something like 15. Not all of them are actually open source databases. There's also stuff from Google, there's Azure Cosmos DB, and so on, but most of them are actual open source databases. And so you would think, oh, great, we have so many options, so many to choose from. There's for sure, there's one among them that is just, woo, you can run it on 1,000 nodes and you can run something like 1 million transactions per second or whatnot, right? It turns out not all distributed databases are created equal. For example, not all of them, if you store a record in the database and you go back sometime later, and maybe you got disconnected from the node on the cluster that you've been connected to when you stored the record. So you get disconnected and the database client connects to another node and it queries the record and it doesn't get it back. Maybe not so good, because in a world like that we may be more familiar with, like on SQL servers with ACID compliance and sequential consistency and all that stuff. I don't know, many of you would probably be familiar with that stuff, more or less. All this is talking about SQL ACID is about single node databases and not about distributed ones. So with distributed databases, it gets even harder to implement a consistent database where if you store data, it basically behaves like you don't have a distributed database with many copies. It just behaves like it's just a single copy, single node, and the order of operation is according to real time. So if one client does a write at one point in time and another client comes in a little bit later, it sees that record and not some previous state. So you can have a million kind of what they call database anomalies, and many of those databases are what they call base databases. So they are not highly consistent. And I forget the abbreviation. Basically available soft state. Yeah, that's it. Base. So one primary example is Apache Cassandra. That's that one over there. So that's an Apache open source distributed database written in Java, and it's kind of probably the industry standard, and it's one of the earliest implementations of an open source database. And so this is in contrast to like an ACID compliant database in sequential mode. This is what they call a base consistent database. It might be available, it might not be available. A record might be stored, it might not be stored. And that's okay for certain things. So suppose if you are Amazon and if you put something in your shopping cart and maybe then you go to, and you forget about it and then you go back to a different machine and you want to look into your shopping cart and suddenly the item you've put there is not there anymore. I mean, the user might complain, but is it really that bad? Does the world melt about this problem? Probably not. So that's why many cloud application and usage scenarios don't really require a high consistency. They get away with this kind of base semantics, right? Now the thing is, this won't work for us. We need something, we need a database that is consistent. And it's coming on the next slides. Okay, this is basically what I already covered. So the requirements that we have for our database, consistency, and we also need locking in a database, which is a bit uncommon. Most databases don't really offer some kind of locking, but given a few database operations it is implemented to implement a distributed log manager, you either need transactions or an atomic compare and set operations. And we need this distributed locking basically to serialize and isolate access to two different resources, file system and database, in order to kind of give this atomic SMB create operations, right? So where a client wants to create a file and we have to make sure that the operations of creating the file in the file system and checking all this file handle state like share modes and oplogs and leases in the database are kind of appear as an atomic and serialized operation to the clients. And so then looking into performance, then the thing is, okay, so there are some databases that have this this consistency semantics that we need, that are strictly sequential or whatever, and we could implement some locking. But the thing is, if they are really highly consistent, they have to replicate records, they have to enforce the order of operations according to real time, and all this just makes them slower. That's why Amazon uses a base database for its shopping cart, and not one that is very, very highly consistent, because it is slower, right? So the problem is, if we look into replacing CityDB, which is very, very fast in storing database records, if we look into using a distributed consistent database, reading and writing from the database will be slower. There's just no way around it. But the question is, does it really matter, right? Because if the goal is, as a product maybe in the future, to have a Samba server just running in the cloud, similar to Azure SMB, users connecting over a slow link to the internet, the connection will be slower anyway, right? So we will have a longer latency, and the typical workload is also not like a high performance HPC NAS that you have running in your data center. It's more like maybe office workers sitting at their desk, double clicking in a Word file and opening that. And it probably doesn't really matter if it takes 200 milliseconds to open it or 400 milliseconds, right? So that would be the idea. And another assumption is that typically those office workers opening office files, they are not working on the same file. They will probably be working on different files, right? So ideally we would have kind of a non-concurrent access pattern to different files, because if you have contention, so if you say you have 100,000 users that are all opening the same file, they will all be hitting the same record in the database. And that will just be slow, and that won't scale with any distributed database, right? So after doing some tedious research and looking into the documentation of many of those databases listed, I came up with like a list of, okay, so which databases might be suitable for doing some performance testing, hooking them up into Samba, doing performance benchmarks, testing their semantics, are they really consistent, and so on. And this is what I came up with. Giving the names for the icons. So this is Ceph, the icon from Ceph, and Ceph uses a distributed database, which is, I think they call it the Rados store. And there's a library, librados, and there are Python bindings and so on that you can use to basically, where the Ceph file system is basically implemented on top of that database. I think, I'll put it another way, this database stores the metadata about the file system, and the file system data itself is stored in an object storage, right? So, but anyway, it's just the metadata database used in Ceph itself for many things, including the Ceph file system. Then, as mentioned before, this is Apache Cassandra. Crap. That's etcd. Yeah, that's etcd. So this is kind of the database used in Kubernetes for storing the Kubernetes cluster state in a persistent way across the cluster. Thanks, Jeremy. This is SkyLaDB, and that's FoundationDB. So these are all open source databases, so thankfully I was able to spin up test systems and doing the necessary development for writing backends, so to hook Samba into the databases and do some tests. Does that work? Oh, it works. Right. And so what I did in order to kind of have a rapid development cycle, so Samba is typically written in C, and writing stuff in C is typically 10 times the line count of, for example, writing stuff in Python. So my idea was, okay, so in Samba we have a database abstraction layer, it's called dbrep. That's written in C, and thankfully there are bindings to integrate from C code to Python code. So that's what I did. I wrote a new backend for our abstract database interface, written in C, that interfaces into Python, and can run and call into a configurable Python script that implements an abstract interface, like give me a record, store a record, lock a record, and so on. And so, all right, I implemented backends for Apache Cassandra, etcd, and so on. And with an amazingly slow file line number count. And the benchmarks. And this is the place where I kind of sat there in tears after all that work. So this is work that I already presented at Samba XP in spring earlier this year. Where kind of, I mean, I could break into tears here on stage, probably better not, but the thing is, we have CDDB right on top here with an insane number of open-close operations per second, right? Going up to 30,000, and it just goes down here because the client is just a bottleneck, because I was at that point just running with a single client, and surprisingly, just 2 days ago, thanks to Volker, I thought I checked before that the client is not the limit. And it's not the limit when using it. One of the other databases said, ooh, where's the pointer? There is it. But when using CDDB, it turns out the client is the limit. So if I run this test here just with more than one client, the number just at some point stabilizes up there. It even goes higher up there. So something like, I saw something like 60,000 opens and closes per second. So really, I sat there in tears because all the other databases are down there. Oh my God. So yeah, forget about it, right? Let's use CDDB. But it's like comparing apples and oranges, right? I said before, CDDB, it just doesn't replicate the record. With this here, SMB persistent handles are not possible, it's not elastic, and so on. So the idea was, we see, well, they are very close together, but the winner is FoundationDB. And supposedly, I think maybe switch to the next slide. So FoundationDB is a key value store. It's not a SQL server or something like that, but it supports transactions, which is good because we can easily implement locking, as mentioned before. We need locking, right? It's supposed to be, and there are some numbers on the website of FoundationDB, really, really scalable. By adding the number of nodes, or they're giving the number in core count. So of course, if you add nodes, you add cores, and they have numbers like, so where is supposed you have 256 cores in your cluster. They have a workload 50-50 reads and writes of, I don't know, it was something like 500,000 transactions per second, which is really insane, right? So I thought, okay, maybe I just didn't have enough nodes in my cluster when I tested FoundationDB. So, right, so I had only 3 nodes. I had a small FoundationDB cluster, and it wasn't really an actual cluster. It was just basically a partitioned VMware ESX server where I had 3 VMs with, I don't know, 4 cores or something per VM, and then put them together as a cluster and said, oh, this now pretends to be a 3-node real cluster, but it wasn't. It was just basically just a partitioned real server, right? So at Samba XP earlier this year, I concluded with, okay, we need more tests on larger clusters, and that's what we did. And here are the results. But before sharing the results, just describing briefly how we did this. And this is the tool that we just learned to use for this. We have never used this before, Terraform. Really, really nice. So I had this idea of, shall I dare it? If I don't know, if we'll have the time, do a demo. So what I do here is Terraform destroy, so Terraform apply. So I would just hit return here, and this will bring up one of the test clusters in Azure, right? And this takes, it depends, 16 seconds, 2 minutes, 3 minutes, takes some time. So I will keep this running in the background, and if we have some time at the end, maybe we can have a quick look. So what's nice about Terraform, we can use this to spin up, in our case, just VMs in a cloud. I'm using, sponsored and hosted by Microsoft, so of course I'm using Azure. And you can easily configure the number of nodes that you want to run, right? So you have maybe 1 client, we want a 3 node CDB cluster, and then we want to test with the different number of FoundationDB nodes in the cluster, right? And it's just like changing a variable, and then thankfully Yule did all the tooling, running scripts, checking, okay, how many nodes do I have, and copying the files across the VMs to have working Samba cluster and FoundationDB cluster. And it took her, I don't know, a week or 2, I would say, of real, not wall clock time, but work time. But in the end, this is really, really amazing stuff, right? So we're just running in the background, then in the end, you have a few files. Infrastructure as code, as they say. And this spins up all that stuff that we need for testing. So what did we test? What was the benchmark? So basically, open and closing in a loop from many clients, right? A configurable number of clients, maybe 1, maybe 2, 10, 100. I mean, I'm giving up a limit of 500. But I was actually aiming at 50,000, 500,000. It turned out the resources I've been using in Azure and the setup of the cluster didn't quite, wasn't really able to sustain that demand and workload number of clients, but hopefully this is just a limitation of me being able to tweak the Azure VMs using the right Azure VMs with not SSDs, but NVMe SSDs, which will be more expensive than using SSDs, and also not really be able to properly configure and tune FoundationDB. So what did we get? Sorry, this is wrong. So this is not comparing CityDB with FoundationDB. This is comparing the initial results that we got from FoundationDB, like getting something like I think something like 3,000 open close per second. And remember, with CityDB, I saw something like 60,000, right? So again, apples and oranges. These are really distributed open close, so you can do SMP3 persistent handles and so on. And so I was able to get a lot more out of it. This curve here. So we get up to something like 12,000. This is with some optimizations that I did not have in the previous versions in the database backend for FoundationDB, and with using larger clusters. So the largest cluster FoundationDB that I tried was, I think, 32 nodes, 4 cores per VM. But the main thing is, so as a database, this is mainly bound by IOPS, by disks. So what you would typically do on to have a really fast and scalable FoundationDB server, you won't add CPUs and cores. You have to add disks. You have to add fast disks. So this was using IOPS capped SSDs in Azure with something like a limit of 6,000 or maybe 12,000 IOPS per second. So with more capable hardware, NVMe disks and so on, which Azure offers, but just I ran out of credits. I couldn't use them, especially if you're spinning up 32 VMs, right? The bill keeps clicking. So, but at least it got quite a lot better. I mean, so 12,000, it's not 60,000, but we are a lot better than previously. So it gives some hope that maybe if we get to better tune the FoundationDB database, if we get to use real hardware, real NVMe disks, and so on, we hopefully might also see the numbers that FoundationDB is putting on their website. Do we have this on the next? Oh yeah, results and conclusions. Yeah, and this is the one that I wanted to point out. So we get something like 12,000 SMB level open and close operation, which translates in the back end of FoundationDB to 44,000 write transactions per second and in the FoundationDB cluster. Yeah, only, well, that's not quite right, 10%. It's like 20%. I mean, okay. So this looks hopeful, right? FoundationDB, maybe, definitely something where more work is needed. And so, I have my finger in front of the laser, it's burnt. So, going back to, okay, maybe FoundationDB is an option. So what about maybe we do ourselves? We maybe just implement a distributed database our own. We rewrite CityDB, maybe using consensus algorithms like Paxos or Raft. We actually tested one of those databases earlier, etcd, for example, is based on Paxos. And the problem is they have basically, they have a single leader in the cluster, and this turns out to be a bottleneck. So maybe do we have what is the time? I'm on slide 52, slide 58. Okay, so we might have time to go back. You remember, etcd down there, right? I mean, that's close to FoundationDB, it's maybe the half. And so, actually, there are options that you can get clever if you want to implement something, a distributed database based on Paxos or Raft yourself. I'm continuing here. So, there's a database called TICV. And what they do, so in Paxos or Raft, typically in a simple implementation like etcd, you just have a single leader and the key space is not partitioned. So what you can do is you partition your key space into different shards, and you then have a consensus leader per shard. And that's what TICV does, and this does scale a lot better, but this is a hard problem. This is a hard problem to do, because then it turns out, so what happens if you change the number of nodes? Then your shards change, right? And that means you need consensus about the shards in the cluster. So the problem becomes hard, and Might be an interesting problem to solve, but the idea again is maybe there's already something that does it for us, like FoundationDB. So, an outlook. I've mentioned Apache Cassandra before, and I kind of said, okay, Apache Cassandra is a base database, so it means you store a record, and then sometimes later you go to the database and say, okay, give me the record, and it says, no, I don't have it. I'm sorry, not this time. Come back later. So currently Apache is on Cassandra is on version 4, and there's going to be a release of Cassandra 5 later this year, and this will ship a new highly consistent implementation of a new consensus algorithm that has been researched and developed recently. It's called Accord, and this is supposed to give interesting properties. Back. Quick report comes out. With regards to, it should be fast, and it should allow also very fast across data centers and availability zones transactions in the cluster. So I'm really looking forward to get my hands on this. I mean, it's Java stuff, but the industry is using it heavily, right? So maybe this is another option, and we just have to look into this as well. We already have the Samba backend for hooking into this, into Cassandra itself. So it's just a matter of waiting for the version, installing it, and then doing some more tests. So, quick. We have this brought up, IO lab, back room, right? So when we are on the cloud, port 445 TCP, try to connect, blocked. Some ISP on your way from your home to the cloud will probably block TCP port 445, so you can't connect. So what did Microsoft do? They did SMB over QUIC to work around this, right? So that's then UDP port 443, right? Something like that. And so this has been kind of something that we've been thinking about in the Samba team. So how could we implement SMB over QUIC in Samba? And that's basically not that easy, because for the interfacing with the network, we use just the socket API, and the socket API on Linux or any other system doesn't support QUIC yet, right? So you can do QUIC in user space, and just Jeremy recently stumbled across a maybe very useful, mature, and for us usable library that implements QUIC that we could use to implement SMB QUIC in Samba. And this is kind of related to, running Samba in the cloud. We might need QUIC. Okay, final summary. So, probably got that across, right? So there's still a lot to investigate. And if you're interested, please feel free and welcome to join the effort. And so, having said that, and before getting to the Q&A, if we have like 5 minutes left or something, we can see if, oh no, I need my glasses. So, apply complete, that's good. So we now got a Samba and FoundationDB cluster in Azure. We just need to run this command to get the IP address of the public IP address of the client machine, also running in Azure, and then connect to this as usual. Hopefully this should work. Hey, looks good. Let's start another tmux anyway. So now what we can do. So this is just the client that I've been using to run this Samba SMB torture benchmark. That's probably most interest, but maybe if we have the time, we can poke around a little bit and maybe look at the CDDB server that should be running the first node on this IP. We can run CDDB status. Whew. Okay, so the CDDB server is up and running. That's good. Now we can also, if we feel like it, SSH to the FoundationDB cluster or one of the nodes. That should be running on this IP address. Right, there we go. Come root. And then we can use the FoundationDB command line client to check the database status. And there we go. Page up a little bit to share the output here. I mean, it's not probably telling you anything really useful for you, but just to show you that it's indeed working and running, and just running some Terraform stuff. You spin up a Samba cluster, you spin up the FoundationDB cluster. And so we can run our benchmark. Let's say, oh, be conservative, just use 10 clients for 30 seconds, blah, blah, blah. Any mistakes? No, looks good. So it opens the connections, runs for 10 seconds, and it's just doing in the background. So we have 10, no, it's one process, but 10 instance, 10 connections in that one process, multiplexed, and it's just doing all those connections are doing open, close, open, close, open, close, hammering the server. Metze, in a second.
You mentioned that you're not testing the same file.
Yes.
Because the name of the test would indicate that.
Yes. Is that something I should explain to the audience? I mean, because you might know that. So the test, basically, yeah, the test uses a single file. So all that clients in this benchmark tool would basically open, close. Oh, 10 minutes left. Okay, the same file, exactly, right? So what I had to do in order to kind of simulate that workload that I'm targeting, which is non-concurrent access to files, we have a VFS module in Samba that you can use to basically make coherent access to a single file, just break it and make it appear like it's a let all access go to different records in the database. Not a single record in the database, which it would typically have. It's all the same file. All clients would just hammer on the same record in the database. So we have a module, file ID, which you can configure, where it turns all, you will have a single record for every connection, right? So they don't stand on their foots. So it's non-concurrent, right? Okay. Keep running. Okay. That's that. And it looks like I'm early. So, yeah. Any questions? Volker?
So, what you're mainly testing, if I get it right, is scalability across tons of connections. Have you measured the basic footprint latency of changing from CQB to FoundationDB?
Yeah, so we have a latency here also in the output. Where is it? I think it's in that window. So we have an average latency. It's the number after num, after operations per second, for the open and the close. I mean, oh wait, I can double click. So it's here, right? So it's 22 milliseconds for the open.
And how does that compare to CQB?
Fucking slow, of course. I mean, we could. Do we have the time to? Well, I would have to destroy the cluster and spin it up again with a different configuration. Where I would not be using the FoundationDB backend, but the default CDB backend. And
about all of magnitude, I mean, is it like
below a millisecond for sure.
Okay.
Yeah. So I mean, on this cluster, I saw like 60,000 opens and close per second, right? So for sure, the latency was. I didn't really pay close attention, but it's maybe 0.1 milliseconds or something in that range. Like we can. I mean. Any other questions that we will have to, where we'll need this cluster for to answer them, and then maybe we can destroy it and bring it back up, or we can do it offline. Yeah.
The point is, the base footprint latency will be a lot slower.
Yeah. As throughput, performance, aggregated, and latency, right? But that was kind of the assumptions, like you're double-clicking word file. I mean, if it takes 1 millisecond. Yeah. I mean, so 20 milliseconds. I mean. For a really persistent handle state in the cluster, I think it's quite good. Okay. Yeah,
Slightly unrelated question. So your goal is to scale the Samba scale, right? Because the connections you still solve that, right? Across a large network. So if you use CTDB to store it, definitely I think this is how you solve that. But I also understand if you have to, let's say the code is you have 100,000 clients connecting you, right? That also maps to 100,000 SMBD processes, right? So that is not a scaling factor today. I mean, just curious, if you can solve that also, right? To scale to, let's say, 1 million clients.
Well, I mean, for that you still will still have to scale the number of nodes in the CDDB cluster, or in the Samba cluster, which is basically not a CDDB database cluster anymore, right? It's so basically an aggregation of nodes running the Samba file server, so SMBD processes. So if we expect something like a 1 million clients, that's 1 million processes. So you will probably need, I mean, how many processes can a single VM run? Maybe 10,000, 100,000, I don't know. So you have to scale up the number of nodes in the Samba cluster for that.
It's a scale-out story, right? I mean, we're not trying to pack in more connections.
Yeah. So it's scale-out and elasticity, right? As mentioned before. With CDDB, it's difficult to add and remove nodes on the fly because you get this full hard stop of the whole database. So if that you are next. If that answers, I forgot to repeat the question. I'm sorry. I can. Yeah. So the question was about scalability, right? So hopefully I answered that. Volker.
I mean, the point was, I think you read our process model that we have one process per client, and we are being asked about this many times. We would like to work on getting multiple clients to a single SMB, and for limited scenarios, it might be possible relatively quickly because we can do multiple TCP connections already. The problem is with all our configuration databases and whatever state and global variables and so on, this doesn't really work.
Yeah,
but I mean, for limited workloads, for limited configurations, we might get something relatively.
In fact, we kind of had a prototype which does this. In fact, we presented it a long time back, 7 years back or so. We didn't follow because we solved the problem also in a different way, scale out and all that. So there is, if you're interested, there is still something we can figure and take it from there. But I guess it's similar story what you guys did with multi-channel, right? So that's what you're going to base on if you have to do something.
Exactly.
Yeah.
The question is, can we actually properly handle completely different clients with completely different user context and so on in single SMB? We're not so sure about this for the general case where you have all include files and SMB and so on.
Idea here was the pool of processes which
sure.
5 minutes left. Yeah. So maybe we can take that offline.
Yeah.
Sorry. Yeah, sure. I'm happy to continue the discussion, but I think there were more questions. Jeremy?
So, in order for people to join it, I know this is asking document how to set this up. If you could put something in a wiki, or you could basically explain, all right, here is the Scaleout Samba website, but maybe,
Yeah, that's a good idea. Yeah, we haven't done it yet, but
you document how you would set this up.
yeah, excellent idea. Yeah, we will do it. We can put it on the wiki or something like that. Yeah, just have the Terraform scripts there, and then just some instructions and.
Nobody knows how to do this.
Yeah. Oh, okay. Thanks. So, any other questions?
You look into like what contributed to the slow performance of other databases. Maybe the client has to make like 10 times more requests compared to CDDB, or is it like always just like one network request?
I mean, so typically, for example, with etcd from the Kubernetes database, it's a key value store. And the request that the client, so Samba, the database client, dispatches and issues to the databases, it's just the same. It's just like, give me a record or store a record, right? So that the access pattern is the same, right? And so I think at Samba XP we already shared some details about this. I already shared a few more details about all the hell that broke loose with all these different databases when I really tortured them. because they are just not designed for this. They are just not designed for 20,000, or no, it wasn't, 1,000 clients that really hammer them with transactions and database operations. That filled up their operation queues, and I got very bad error messages. So error messages that I interpreted as very serious, like database corruption and stuff really broken, for example, in etcd when I hammered it. So yes, I looked into this a little bit, but working with distributed databases is time-consuming. It's hard. Understanding the database, installing, tuning, what is it designed for, what are the consistency semantics implemented by the database, and so on. So yeah, there's room for more research, I would say. Yeah. Okay. Any other question? Okay. So, thanks a lot.